So we're on to our second origin theory for the solar system, and we're hoping that this one, the condensation sequence theory, explains the planetary types that we see, the terrestrial planets and the Jovian planets, and explains the space debris. So let's talk again what we're trying to explain with this theory. When it comes to the planetary types, we're trying to explain the fact that in our solar system, there are terrestrial planets that are inner or closer to the sun. They have higher densities, they have no rings, and they have few moons as well. And then there are outer planets, the Jovian planets, that have quite low density, and they have plenty of rings and plenty of moons. We're hoping that our theory can explain those two things, the condensation sequence theory. So let's see how it does. The condensation sequence theory is really based on density. So it will explain and it will look at the rings that are present in the outer planets, the Jovian planets. But really, it's explaining the density difference between both sets of planets. And the theory is based on the fact that that density variation actually started when the solar system was first moving from the nebula cloud into the disk. Now, 100 million years later, you have these very dense planets closer to the sun, and you have the gas giants farther out from the sun, but they all started while the nebula was contracting from the first dust that started to consolidate. And we've gone over this solar nebula theory about that nebula cloud, and the condensation sequence theory just dovetails on top of the solar nebula theory. It just extends it. So it starts with the solar nebula theory and extends it. And solar nebula was saying that the planets grow from the gas and the dust in the disk. And that's not detailed enough to talk about the differences in the planets. When we talk about the condensation sequence theory and the density differences, we are starting with dust grains that act as what's called condensation nuclei. If you take my climate and meteorology class, you talk about condensation nuclei a lot. So this is from that class. And a condensation nucleus can be a speck of dust that literally you cannot see. That's how small the dust grains are. And they become these platforms for other specks of dust to stick on and start accumulating, so that when we talk about climate, we talk about invisible dust particles that act as platforms so that you can add other dust particles and water vapor to it to form a cloud droplet, and then eventually you will form a rain droplet. The same thing happens here. You're literally forming what is known as planetesimals that are a centimeter or 2 centimeters in diameter over a lot of years. Millions of years is one estimate to get to these planetesimals. And you're basing that on the fact that this nebula has formed a protoplanetary disk, a disk before planets form, protoplanetary, and the areas that are near the center are hotter because the rotation is a little bit faster there and there's more mass there. And so those are warmer. This is before the sun lights. And the areas that are farther away from what will become the sun are cooler. So we talk about condensation as having these dust particles attract elements and compounds that can condense on the specks of dust. And so condensation occurs when a gas cools and changes its state from gas to liquid and to solid, these three phase changes, to become tiny solid particles. And in doing so, we find a really beautiful graph that we can put together. And what it says is this. This is planetary formation temperatures in Kelvin, and that is the temperature of space where the planet is going to form. So let's talk about it. If you are closer to what will become the sun, you have a warmer environment. You have a higher temperature in Kelvin. Okay, so this is the dependent axis of your graph, and your temperature is going to be dependent on your distance from the sun, which is your independent variable. And look at this. Mercury is very close to the sun, and it has a very high temperature of formation. And when you look at Venus, Venus is a bit farther away from the sun, and it has a bit lower temperature of formation. I'm going to go back here for a moment. And then when you look at Earth, a little bit lower temperature of formation for the Earth, a little bit farther away from the sun. When it comes to the Jovian planets, they are much farther away from the sun. This is Jupiter right here. And the others, Saturn, Neptune, Uranus, are farther away from the sun, and they have a lower temperature out there. There is also an ice line that forms here. Remember, this is Kelvin, and Kelvin is 273 degrees on top of Celsius, because Celsius, as you remember, is 0 at the freezing mark of water. But Kelvin says that 0 is when nothing in the universe can vibrate at all. So it doesn't just count water for Kelvin. Kelvin counts molecular energy. So at 273 degrees Kelvin is our freezing line for water. And look, you get to ices right around the Jovian planet formation temperatures. So this is an ice line where vapor in the nebula can freeze directly to ice. It's a process called deposition. Again, if you take my meteorology class, you'll be hearing all about deposition, where vapor goes right directly straight from vapor to ice. And you see this sometimes as frost on the ground that goes directly by that process of deposition from water vapor in the air to frost on the ground. Now, another reason that this graph is so special is that it looks at not only the temperatures of the planets at their formation, but it looks at the temperatures of the condensation temperature of various substances. And you're comparing the condensation temperatures when a metal can go from vapor directly to solid at what temperature, when a silicate, which is a compound of silicon and oxygen, basically making up types of rocks, can go from a gas directly to a solid, when feldspars, which are silicates with calcium or potassium or sodium added in, can do that, when troilites, iron plus sulfur, can do that, when water can do that, we know when water can do that at 273 degrees Kelvin, and when ammonia can do that, which is actually ammonia ice forms lower than water ice, okay, at about 100 degrees Kelvin. Let's go back to the metals. The metals are actually amazing that at these huge temperatures of 1600 degrees Kelvin, that very structured metallic compound goes directly from vapor to solid. And that is very hot. And oh, by the way, that's right around the temperature of formation of mercury. And consequently, mercury has a very high percentage of iron and nickel in its core, which, as you studied before, the core takes up a lot of the volume of mercury. Now, when we get to Venus, we're talking about silicates, which are rocky materials, silicon and oxygen, not really heavy duty rocky material. And those silicates actually condense right at about 1,000 degrees Kelvin. And guess what? Venus, that formation temperature was rated around 900 degrees Kelvin. So Venus is mostly silicates. And I also wanted to point out to you that our situation on Earth is troilite, which we have a combination of iron and sulfur on Earth, which forms our core. That actually condenses at 680 degrees Kelvin. And look, we are right there at temperature of formation at about, right around 700 degrees Kelvin there. So these feldspars condense right on this line right about here. Really remarkable chart there. I hope that you like that. And you'll note in here that the Jovian planets are made up of a lot of water ice and ammonia ice and methane ice. Pluto, all the way out and now a dwarf planet, is made up of argon, which condenses out at a relatively low temperature because it's more of a gas, so it has more energy. Whereas a metal is highly structured, it will condense out at a very high temperature. Check that out in the text and review it so you understand it a bit more. This condensation sequence says that these closer planets, these inner planets, are going to be rockier and the outer planets are going to be icier. And then millions of years later, we have ice and gas giants outside in the outer planets and rockier planets on the inner section. So that, just to sum up, where temperatures were high, metals and silicates could condense easily to form solid planets, and where temperatures were low, gases were able to condense out there. And obviously our nebula is formed from a unthinkable amount of gases, so there were many more ices than silicates to condense in the outer solar system. When we talk about this condensation sequence, we have explained the density differences there. We really didn't explain the difference in rings. So we have to work on that a bit. Fortunately, we have other theories, and we're going to go to those on the next video.